Lesson 8, Voltage. Part 1, Electric Potential Energy. We'll start this lesson by reviewing some of the concepts from gravitational potential energy. Gravitational fields are given by the symbol little g. Gravitational fields are associated with gravitational potential energy. Recall from Physics 20 the formula for gravitational potential energy is EP equals mgh, where m is mass, g is the gravitational field, and h is how high you've lifted the object. So you can see that gravitational fields are contained in the gravitational potential energy formula. A change in potential energy is called work. We would write this as change in energy equals work. And recall again from Physics 20 the formula work equals force times distance. This formula tells us that in order to change the potential energy of an object or apply work to the object, a force must be exerted. You can think of potential energy or increasing potential energy like stretching a spring. In order to increase the potential energy of an object, you should always feel a resisting force that's trying to prevent you from doing that energy increase. Sort of like if you were to stretch a very tight spring. When you increase the gravitational potential energy of a massive object, you should feel like you are exerting a force against the gravitational field. This means moving the mass in the direction opposite to the way it wants to go. You don't need to exert a force to decrease the gravitational potential energy of a massive object. If you release a mass in a gravitational field, it should immediately start to move so that its gravitational potential energy decreases. In other words, if you let go of an object, it will fall. So, to increase the gravitational potential energy, you move it against the field. So, I'm going to draw a diagram of the surface of the Earth, and we know that the gravitational field lines point at the center of the Earth, and on the surface of the Earth, this points down. If I want to increase the gravitational potential energy of an object, I need to move it against the field. So in the opposite direction to the field lines. If I want to decrease gravitational potential energy, I move it in the same direction as the gravitational field lines. So in this case, it's moved downwards. It's very similar for electric fields. Electric fields are associated with an energy called electric potential energy. When you increase the electric potential energy of a charged object, you should feel like you're exerting a force against the electric field. This means moving the charge in the direction opposite to the way it wants to go. This is a little more complicated for electrical potential energy than it was for gravitational because we have the two different types of charges. So I'll draw a situation in both cases where I have a negatively charged object. We know that electric field lines point at negatively charged objects and away from positively charged objects. Now, if I place a positive charge in that field, if I want to increase the electric potential energy, I move it against the field lines. This is opposite to the way that it wants to go. It wants to go towards the negative charge, but I increase the potential energy by moving it away. If I have a negatively charged object, I increase its potential energy by moving it in the same direction as the electric field lines. This is, again, the direction opposite to the way it wants to go. There's a repulsive force pushing against the negative charge, so I have to apply a force to make it move in that direction, thus increasing the electric potential energy. You don't need to exert a force to decrease the electric potential energy of a massive object. If you release a charge in an electric field, it should immediately start to move so that its electric potential decreases. So again, I'm going to draw a situation where we have a negative charge producing an electric field. The electric field lines point at the negative charge because this is the direction a positive charge wants to go. If I want to decrease the electric potential energy of a positive charge, I move it in the direction that it will automatically go. It's attracted to the negative, so it moves towards it, and its electric potential energy decreases. For a negative charge, to decrease its electric potential energy, you move it in the direction it wants to go. In other words, in the opposite direction to the electric field. Part 2, voltage. Voltage is a concept closely associated with electric potential energy. Voltage is sometimes called electric potential difference, or even shortened to electric potential or potential difference. So if you don't see the word energy, when you see the word potential, what it's referring to is voltage. Voltage is the amount of potential energy a 1 coulomb charge would gain if it was moved from one location to another. The symbol for voltage is capital V. Be really careful because this is often confused with small letter v, which is associated with velocity. The unit for voltage is the volt, also a capital letter V, but it also can be given in the derived unit, joules per coulomb. The formula for voltage we're going to use is voltage equals change in energy divided by charge. Be careful for this because we already have used E twice in our study of electrostatics. The E in this case doesn't have the vector arrow over top, so the E in this case is energy. And it's not just any energy, it's the amount of energy a charge would gain, so it's change in energy. Q is the amount of charge measured in coulombs. Electric potential is a scalar term. Direction does not matter. Example: if 5 microjoules of energy is required to move a 1 microcoulomb charge in an electric field, then the potential difference between the 2 points is, so we have a change in energy equal to 5 microjoules, and we have a charge equal to 1 microcoulomb. We're looking for the potential difference, remembering even though we see the word potential, because it doesn't have the word energy, that means we're talking about voltage, not potential energy. Now, voltage is given by change in energy over Q, which is 5 microjoules divided by 1 microcoulomb, and we get a voltage of 5 volts. The second example, a proton increases speed from 1 meters per second to 4 meters per second in an electric field. Through what voltage did it move? So we have an initial velocity of 1 meter per second and a final velocity of 4 meters per second. This is a time when the symbols start to get a little bit confusing, and that's because voltage and velocity both use the letter V. Voltage is a capital V and velocity is a small v. I'll distinguish my small v's by making one side a little bit curly so you can tell the difference. The mass of a proton is given on your formula sheet to be 1.67 times 10 to the negative 27 kilograms. The charge of a proton is 1 elementary charge. This is 1.6 times 10 to the negative 19 coulombs. So we're going to start by calculating the change in energy. The change in energy will be given by the final kinetic energy minus the initial kinetic energy. So this is 1/2 mvf squared minus 1/2 mvi squared. The change in energy is 1/2 the mass of a proton times the proton's final speed squared minus 1/2, again the mass of a proton, times the proton's initial speed squared. This gives us a change in energy equal to the final kinetic energy, which is 1.336 times 10 to the negative 26 minus the initial kinetic energy, which was 8.35 times 10 to the negative 28 joules, and a change in energy equals 1.25 times 10 to the negative 26 joules. Now that we have the change in energy, we can calculate the voltage. Voltage is equal to change in energy divided by Q. Which equals 1.25 times 10 to the negative 26 divided by the charge, which is 1.6 times 10 to the negative 19. This gives us a voltage equal to 7.8 times 10 to the negative 8 volts. An alpha particle is placed in an electric field with a potential difference of 100 volts. If the alpha particle is released within the field, what is the maximum speed that the alpha particle could attain? The alpha particle is found on your formula sheet in the particles section. The charge of an alpha particle is 2 times the elementary charge, and the mass is 6.65 times 10 to the negative 27. So the charge is equal to 2 times the elementary charge, which is 2 times 1.6 times 10 to the negative 19. This gives the charge for the alpha particle to be equal to 3.2 times 10 to the negative 19 coulombs. We're going to be using the alpha particle a lot in Physics 30 because it's a common particle to be found in study of atomic and nuclear physics. Since voltage is equal to change in energy over Q, we can find the change in energy to be equal to QV. Now, the change in energy is the EK final minus the EK initial. But since the particle was originally just released, it was originally not moving, which means its initial kinetic energy is 0. And the change in energy is just EKF. This means EKF equals QE, or 1/2 mVF squared equals QV, which gives us VF equals the square root of 2QV over M. We're going to use this derivation quite a lot. It comes up quite often when you're dealing with particles moving in electric fields in Physics 30. So I'll move over here because I've rounded a space. The final velocity equals 2 times the charge of the alpha particle, which is 3.2 times 10 to the negative 19 coulombs, times the voltage it moves in, which is 100 volts, divided by the mass of the alpha particle, which is 6.65 times 10 to the negative 27, which gives us a final velocity equal to 9.81 times 10 to the 4 meters per second. Since particles in physics tend to be very, very small, it doesn't take a very large voltage to make them go extremely fast. In this case, it only took 100 volts to make the alpha particle accelerate to a speed of 9.81 times 10 to the 4 meters per second, which is extremely fast. Energy versus electric field. This is an important warning you need to remember. Energy is given by the symbol E. Electric field is given by E with an arrow. There's going to be a lot of times in our study of electrostatics where a formula is going to contain both E as in energy and E as in electric field. This is similar to us running into trouble when we have V as in voltage and small letter v as in speed or velocity. So watch your symbols and notation because it's going to matter in the future. We're also going to examine a new unit of energy. The electron volt is a new unit of energy. This often confuses students because it contains the word volt in it, but it's not actually referring to voltage at all. It's referring to energy. It's a unit that's intended to replace the joule. It is the amount of energy an electron would gain in 1 volt potential difference. So, since voltage equals change in energy over Q, the change in energy equals QV. So an electron volt is given by the change in energy. An electron, which has a charge of 1.6 times 10 to the minus 19 coulombs, would gain in 1 volt. So this is equal to 1.6 times 10 to the negative 19 times 1 volt. So the change in energy an electron will gain in 1 volt potential difference is 1.6 times 10 to the negative 19 joules. This is an electron volt. 1 electron volt equals 1.6 times 10 to the negative 19 joules. The electron volt is very small. We will use electron volts instead of joules when dealing with very small amounts of energy, like the energies associated with small particles. You'll notice that the electron volt is on your formula sheet under the section constants. It tells you 1 electron volt equals 1.6 times 10 to the minus 19 joules.